Welcome, Physics C students. We're going to talk about complex circuits today involving capacitors and how to fill out a capacitor chart. We're going to start by looking at some examples of complex arrangements. Complex arrangement is three or more capacitors that are in a variety of configurations, series and parallel at the same time. So what kind of words would we use to describe these various configurations that you see below you? For this first one, I would say that I have one capacitor in series with two in parallel. Right? The first one is in series with the next two, which are in parallel with each other. For the second example here, I would say that I have one capacitor in parallel with two in series. That top one is in parallel with the bottom two, which are in series with each other. In the next configuration, I would say that I have two capacitors in parallel in series with another two in parallel. You can see these arrangements are starting to get a little bit more complicated, and I don't know that you might see something like this, but you're not going to see something much more complicated than this. And in this last example, what do we have? We have two capacitors in series in parallel with another two in series. Right? Two in series in parallel with another two in series. Okay, so those are some of the ways that we would describe these capacitor arrangements. Now, in general, for a capacitor chart, what you're going to want to do is it's an organizational device that'll help us determine the values of capacitance, charge, and voltage on each capacitor in one of these complex arrangements. First thing you want to do is find the equivalent capacitance of the entire circuit. What one capacitor could replace the 3 or 4 or 5 that you have in the circuit? Once you know the equivalent capacitance for the entire circuit, you're going to find the charge that would be on that equivalent capacitor based on the voltage from the source, the battery, whatever it's connected to, and the equivalent capacitance. Then you'll kind of work your way back through the circuit, finding the individual values of charge and capacitance. Now, if a capacitor is connected directly to the battery, like both sides of the capacitor connected directly to the battery, it's going to have the same delta V, not the same delta V. The heck? Same. If I can edit that. It's a shame this made it into the video. Same delta V as the battery. So what do I mean by if something's connected straight to the battery? We're going to have an example of that here. It's not in the drawing, but you're going to add this in. This circuit here is going to be connected to a 100 volt source. And you can see that this capacitor right here is connected straight back to the battery. So I already know that it's going to have 100 volts on it. And if I know the capacitance and I know the voltage, I can find the charge on that capacitor without even having to do any equivalent capacitance work. That's not the case down here. This capacitor is not connected straight back to the battery. This one is connected straight to one side of the battery, but this is not connected straight to the other side of the battery. So none of these capacitors are going to be at 9 volts. However, if a capacitor is the only capacitor connected to one side or the other, then it's going to have that Q equivalent stored on its plates. So in this example right here, this capacitor, this one plate, which is connected straight back, this one plate would have the equivalent charge on it. This will make a little more sense when we start breaking these down in the following examples. Things that you want to keep in mind and like pretty much absolutely know, have these memorized, is that when you're in series, capacitors have the same charge but different voltages. And when you're in parallel, they're going to have the same voltage and different charge. So on the next page, these two are in series. And if they're in series, they're going to have the same Q. If we have two of them that are in parallel, these ones will have the same delta V, but different Q. These ones here have the same Q and different voltages. These two here are going to have the same V, but they'll have different Qs. Okay, keep that in mind. Very important patterns to remember. So we're actually going to start with the bottom example here, and then we'll go back up to the top one. In this bottom example, the first thing that I want to do is find the equivalent voltage for the entire thing. And I'm going to label my capacitors. Now I'm going to label this one C2. This one's going to be C4, and this one's going to be C6. I'm going to change this here to C4. I'm going to change this one to C6. And we can see that those kind of match up, right? 6, 6, 4, 4, 2, 2, just to make it easier to talk about these. So I know that these two here are in parallel, right? So I could draw out an equivalent circuit. I would have my 9 volts there. I would have my C6 down here. And then up here, this I'm going to call C24, because it's the equivalent capacitance for numbers 2 and 4, right? This is one capacitor which replaces those two. And we would want to use the parallel rule there. The parallel rule for capacitors is pretty easy, right? C24 is going to equal C2 plus C4. So all I need to do is add those together. 2 microfarads, 4 microfarads. I'm going to get 6 microfarads. Now I've got my 9 volts. And now I'm going to find one capacitor, CEQ. And that one capacitor, now I have to use the series rule. The series rule is that 1 over the equivalent capacitance equals 1 over C6 plus 1 over C24, right? It is this one and this one together making the equivalent. If you do the math here, you will find that CEQ is equal to 3 microfarads. The math there would look like 1 over CEQ equals 1 over 6 microfarads plus 1 over another 6 microfarads, right? And that's where we get that from. So I can fill out parts of my chart right now, right? I know my equivalent capacitance here was 3 microfarads. 3 microfarads. It's going to have the full 9 volts to it because, again, it is the only one connected straight back to the battery. So it's going to have 9 volts on it. I know that C6 was 6 microfarads. C2 is 2 microfarads. And C4 was 4 microfarads. Do I know the voltages on any of these other capacitors? No, because they're not connected straight back to the voltage source on both sides. What I do know is that if I went around the circuit, this plus this would have to equal that 9, right? So C4 and C6, those two have to equal the 9 volts together. Or I could say this one and this one have to equal 9 volts together. But now that I know 2 of these, I can find the third one, and I would find that third one, I'd find the charge equivalent by doing this. C equals Q over delta V. I want to find Q, so Q equivalent is going to equal C equivalent times delta V equivalent. And that's going to be my 6 microfarads times, my equivalent was not 6, my equivalent was 3. That's going to be 3 microfarads times 9 volts. And that's going to give me 27 microcoulombs. Now that I know that's 27 microcoulombs, this plate right here, which is connected straight back to the battery, has to have Q EQ because it's the only plate. So I know that this is going to also be on C6, 27 microcoulombs. So I know Q6 equals Q EQ. Now that I know 2 of these, I can find the third one again by using this kind of relationship. In this case, I'm looking for a voltage, right? So I can say that delta V6 equals Q6 over C6. Q6 over C6. So Q6 was 27 microcoulombs. C6 is 6 microfarads. And when you work that out, you get 4.5 volts. That 4.5 volts goes here. 4.5 volts. And as soon as I know that's 4.5 volts, I know that C6 plus C4, right? Or I should say V6 plus V4 is going to equal the volts of the battery, 9 volts. So if this is 4.5, both of these also have to be 4.5. And now that you know 2 of these, you can find the third. If you know 2, you can find the third. And again, I would find the third by using this type of rule, but applied to numbers 2 and numbers 4. So that's Q equals CV. So Q4 equals C4 times delta V4. which is 4 microfarads times 4.5 volts. And 4 times 4.5 is sorry, I lost my train of thought here. 4 times 4.5, that's 18 microcoulombs, okay, for Q4. That's going to be 18 microcoulombs. And now there's two different ways that I could find Q2. There's two different ways that I could do this. One, I know that these two together have to equal 27, right? This and this together are connected straight to the plate. And so those two are going to equal the equivalent charge, right? This and this have to equal out to that. This has to equal out to that. So 18 and 27, I know this is going to be 9 microcoulombs because they have to add up. The other way that I could do that is here. I could say Q2 equals C2 times delta V2, which is 2 microfarads times 4.5 volts. And look at that, I get 9 microcoulombs. 9 microcoulombs. So that is how we fill out this chart. Let's just look through the whole process again quickly. Okay? I started by using the parallel rule, finding the equivalent capacitance. Then I used the series rule to find the one capacitor, right? The one capacitor to rule them all. I find the equivalent capacitance. Then with the equivalent capacitance and the battery voltage, I can find the equivalent charge. This one plate is connected straight back to the battery, so I know those two have to be the same. Once I know two of them, I can find the third. And then I know that that these have to add up to 9 volts. These would also have to add up to 9 volts. And then once you know two of them, you can find the third. And I know that because these two plates are connected straight back to the battery, that those two together have to be the same as the equivalent charge. Okay? So let's look at a second example here. And this example up top, we connected it to a 100-volt source. And the first thing that we need to do is find the equivalent capacitance, right? So I do have a parallel arrangement here, but this one is not in parallel with one other. So I'm going to have to start off using the series rule to begin with. And I'm going to find a circuit like this, right? It's going to have one capacitor here, one capacitor here, and then the battery over here. Always try to make one line shorter on the battery. That's 100 volts. This would be C2. And this I'm going to call C31. So this is C3, this is C1, this is C2. You can probably see how I named those, right? So C1 was 10 microfarads, C2 is 2.5 microfarads, C3 was 0.3 microfarads. I know the entire battery has 100 volts on it. And I need to find the value of C31, right? And that's a series arrangement. So I can say 1 over C31 equals 1 over C3 plus 1 over C1. That gives me 1 over C31 equals 1 over 0.3 microfarads plus 1 over 10 microfarads. And when you work that out, you will find that C31 is equal to 0.29 microfarads. Now I need to take this and find one capacitor here that is connected straight to my 100 volts, and this would be CEQ. And CEQ is going to equal C2 plus C31. The parallel rule is always easier because you just add them together, right? So I'm adding together those two to give me that one. So this is going to be pretty straightforward. C2 was what, 2.5? Yes. 2.5 microfarads plus 0.29 microfarads, and I get CEQ equals to 2.79 microfarads. 2.79 microfarads. So we can put that up in our chart now. 2.79 microfarads. And you're going to work your way back through the circuit now. I'll give you some patterns to use, but you're going to be doing this mostly on your own. Once you know two of these, you can find the third one using C equals Q over delta V. So find that equivalent charge first. Then I know that this capacitor right here is connected straight to the battery. So it's going to have 100 volts on it. So that's for number 2.5. This is going to be 100 volts. And if I know two of them, I can find the third, right? I also know that that these two together here have to be 100 volts total. So I know that V3 and V1, those two together have to add up to 100 volts. I also know that those two charges, Q3 is going to equal Q1 because they are in series with each other, right? So different voltages, different delta V, same Q. Okay, so you're going to finish off the rest of that chart on your own, and we'll check the answers in class. I look forward to seeing you soon. I hope you have a good night, evening, morning, whatever time of day it is. See you around.